and welcome to the Fall 2017 Capstone Symposium. We're Team Bose, and our project is Personal Radar. On our team, we have 2 computer engineers, James Kiesling and Christian DeVideo. We also have 2 electrical engineers, Benjamin Welch and myself, Marjorie Pickard. Leading our team is our technical director, Stephen McDonald, and our consulting technical director, Mike Smith. When people think of radar, they typically think of weather forecasts or military applications. But radar is actually a very versatile sensor. Recently, it has been integrated into the design of autonomous cars, where it measures the distance between vehicles, as well as watching out for pedestrians or objects in the road. This inspired Bose to create this project, which investigates whether radar technology has reached the point where a personal wearable radar device is feasible. A personal radar would allow users to navigate around objects in his or her environment. This has many applications, such as helping the visually impaired, as well as distracted pedestrians. For Bose, this is an exploratory project. They want to assess the viability of personal radar for possible future integration into future products. By the end of next semester, we would like to have a working personal radar device. It needs to be fully portable. That means that it is small and light enough to be worn by the user. It also needs to be able to recognize objects in its environment, telephone poles, trash bins, an incoming car, and then track those objects and warn the user of potential collisions. We are using the new Distance to Go radar board created by Infineon Technologies. It uses FMCW radar, which measures both distance and velocity of targets. The first task was to establish serial communication with the board. This means taking radar data from the board and importing it into MATLAB, where our object detection algorithm would recognize objects, track them, and predict collisions. Then it would warn users of these potential collisions. Finally, the entire system needs to be packaged small and light enough to be worn by the user.
So this semester we accomplished 5 main tasks. The first of which was researching the health effects of 24 gigahertz radiation from our board on the user. So using the IEEE safety guidelines, we found that because of the high frequency and low energy output of our board, there would be very low deep tissue risk. However, because the board would be worn so close to the user for such a long amount of time, we do recommend some type of RF shielding. Next, we wanted to test our radar board in the real world. So we went into a wide open field to decrease background noise and used a radar reflector at different distances and angles to measure our radar board's accuracy at measuring distance, velocity, and also its field of view. From this experiment, we found multiple deficiencies in our radar board's default configuration, which we will need to improve in the future once we need to collect more accurate data. We will also like to improve our experiment in the future so we can collect our data more effectively.
So, after performing our initial field experiment, we decided that we wanted to visualize the data we obtained during that experiment in MATLAB. During the experiment, we were able to visualize the data in real time, as well as save that data for future use directly from the GUI provided to us with the board. In order to visualize this data in MATLAB, we simply needed to read the corresponding output file and port that data into MATLAB and plot it. Initially, we wanted to visualize this data in MATLAB in order to get a better understanding of the data we're working with, as well as the system as a whole. However, after doing this, we decided that in the future, our best course of action would be to use the raw data obtained directly from the board via serial communication in order to extract relevant target information and develop our collision detection algorithm. In addition, we also researched existing automotive radar algorithms. We did this because the application of automotive radar is so similar to what we want to accomplish with our project. We researched collision detection algorithms as well as FMCW chirp parameters. and then we assessed whether or not we would be able to use this information and adapt it to fit the needs of our project. In the future, this should prove to be very helpful when we begin to develop our collision detection algorithm. This image that you can see is just a simple visual representation of the collision detection algorithms we were researching. In this example, peaks in the magnitude of the plot correspond to objects being detected at that range.
So the initial hurdle we faced when interfacing the board with the rest of the system was establishing serial communications so we could feed real-time data to the object detection algorithm. So we had to reconcile existing serial communication in MATLAB with these proprietary Infineon protocols in the firmware. So because of the relative newness of the board and the limited external documentation on it, we had to do like a fair amount of reverse engineering on this board. And so at the endpoint, we were left with a MATLAB GUI that could show you the data in real time, similar to the one provided us by Infineon. And along the way, we documented various aspects of communication, so implementing further features down the road won't be so difficult. So how do we define the optimal tasks that we need to complete next semester? So first, the object detection algorithm, which is in essence the heart and soul of this project, needs to detect and track multiple objects within the radar's field of view, determine if they're going to provide a threat for the user, and then alert the user to avoid this situation. So it needs to differentiate between whether the user is going to walk into a telephone pole or simply walk right by, which is going to be one of the more difficult cases to establish in the algorithm. So next we need to make a radar simulation in MATLAB. So firstly, with the simulation, we need to reconcile it with the real-world data we've taken, ensure that it's correct, and then from there, we'll be able to save a lot of time by testing various real-world situations and variables without having to go out and take actual data really as much as we would have normally. And we'll implement that in MATLAB, so it'll be easier to interface with the rest of the system already implemented in MATLAB. Finally, we just need to integrate the entire system into a wearable device. So it needs to reliably mount the board to the user so we can get reliable data, as well as putting a battery in there and making it totally portable. And we also need to determine what type of notification we want to send to the user and what level of notification. Do we want vibration, sound, phone notification, and what level? So do we want simply yes or no, there's something that's going to collide with you, or do we want different levels of alert that would help the user determine the urgency of the situation? And finally, as mentioned before, we just need to provide some kind of shielding on the back of the board, just to prevent any kind of questions about long-term use of the board, and we don't have to worry about any kind of health hazards that might arise. So finally, as this comes to a close, we just want to thank everybody who made this project possible, namely our technical directors, Mike Smith and Stephen McDonald, without whom it would not be possible to get where we are today, as well as Dr. Sunak for his tireless work putting together the Capstone program as a whole and this amazing Fall 2017 Symposium. Thank you.
Thank you.